Okay, this is section 5.2c. Begins on the bottom of page 246. This is a very, very small leap. It's not really a leap. Step forward from what we've learned so far about radicals. We've been dealing with them for 2 days now. And so it shouldn't be very difficult for you to do. What we're going to do is we're going to add variables into the mix. And variables that have powers on them behave just like numbers that are powered like. I erased it over there, but like the 8 was 2 times 2 times 2, we could write that as 2 to the 3rd. So now we're going to see things like x to the 5th and y to the -7 and stuff like that inside these radicals. We're going to try to deal with those, but the rules still apply. So, except for one extra one, there's some rules down at the bottom of page 246, and the discussion of it pretty subtle when you start adding variables. Because when you start adding variables, the problem becomes we don't know whether those variables are positive or negative. They're just numbers, and we don't know what their signs are. When we see the number 8, we know it's positive. Or if we see the number -8, we know it's negative. But when you see the number x, what replaces it or what it could be positive or negative. And that causes problems because you remember you can't square or you can't even root a negative number, right? You can even or you can odd root a negative number. So that creates a little bit of a problem. So consider this with me for just a minute. Just consider square root since that's something you're used to. If I have the square root of, let's say, 32 x to the 5th, y to the 12th. Let me make this a 4. No, make it a 6. Okay, and you want to simplify that. You've got to find the pairs, and one of every pair comes out because every time there's a pair, you got a perfect square, right? One of every pair comes out. 32, I think you can remember. I don't know. Does anybody remember how that factors? 3 2s or 5 2s. So I'm going to take out a 2 and a 2. 3 x's. You see 3 pairs in there? It's x times x times x times x times x times x. You see it? And how many y's?
6. Yeah.
6. Do you want to see it? Does anybody want to see all the pairs first time around? Yeah? You want to see what's going on? Okay. So what this really is, and this is going to get lengthy here pretty quick. But what this thing is, when I simplify that 32, if I write down everything that's in there, I have 2 times 2 times 2 times 2 times 2. That's your 32. Okay? Yeah? And then I have an x and an x and an x and an x, x, x. That's going to get twice as many y's. Your hand doesn't want to make that pattern that many times. It's hard to make it keep going. Let's see. 2, 4, 6, 8, 10, 12. Okay, so this is literally what we have. I did not expect to see this on your papers. I don't expect you to do this. I expect you to grab onto this idea of seeing these numbers up here and deciding how many pairs there are. But there's a pair of 2's here and a pair of 2's here, and that's the lonely little guy gets left out. I got a pair of x's, x's, x's. So one of every pair is going to come out. But this is x squared, whose square root is x. This is x squared, whose square root is x. And this is x squared, whose square root is x. And I've got 1, 2, 3, 4, 5, 6 pairs of y's. Did you follow all that? So I've got y squared 6 times. And when I square root of y squared, I get a y. So I've got 6 y's coming out. You understand? So I've got a 2 and a 2. I'll just go ahead and write down what I've got. And by the way, everything that comes out multiplies. So I've got 2 times 2. And I've got an x, x, and an x, and 6 y's. I'm just doing this really, really detailed here. And a lonely little root 2. He's the only guy that get paired up. He has to stay in there. So what I have is 4, x to the 3rd, y to the 6th, root 2. And here pretty quick with your understanding that you have, you should be able to get from here to here after you've done that without all this junk in between. But this is really what's going on. You're just imagining all those things and pulling out what you can. Is that okay? Everybody understand that? Here's the problem. When this x in here was to the 6th, it would not matter if this x right here was positive or negative because we're even powering it. So there's no trouble square rooting it because that thing is forced to be a positive number in here.
Can we need all boys basketball players to go to the gym for pictures. All boys basketball players, please hurry to the gym for pictures.
Okay, so this thing right here could have been a -7. To the 6th is still a positive number, which we can square root, so that's not a problem. See what I'm saying? This could have been positive or negative, doesn't matter. And it would have had a positive value in here. When they come out, this thing right here, when we actually took the x's out, if it was a negative number, then this would be negative on the outside. Right? And so this whole result out here would be negative. This would still be positive, regardless of the sign on y, because it's to the 6th power when it came out. But this is odd, which means that if x were negative in here, it's now negative out here, and we now have a negative result, right? But they told us you have to square root, and when you see this symbol, you can only report the positive aspect of it. Remember the principal square root idea? And so, when we do this, you have to put absolute values on that to force the issue. You don't on this, because it's going to be positive no matter what. But this one could be positive or negative when it comes out because of the odd power, and you have to force it to be positive to get the correct answer. And that's really subtle, right? Isn't that crazy? Yeah. Now I'm going to do another one for you that doesn't have, that's a little bit different than this, and show you why you don't need them. I know. So hang on, and then I will summarize the rule for you. But you understand that this has to be forced to be positive because it could be positive or negative. This is forced to be positive because of the evenness of 6. So we don't need absolutes on that. And if you put it on there, it's redundant and wrong. But this needs it. 4 is 4 no matter what. So that guy is the only one that has to be absolute value. Okay, I'm going to erase this because it's taking up too much space. If you have something like this, the cube root of, we'll do something easy like 27 x to the 8th, y to the 10th. Now we're cube rooting. Keep in mind, we're looking for triples now. Triples. I'm going to show you a little thing. I call it bookkeeping. It's just keeping track of what you pulled out and what's left as you do this in your mind rather than do it this way with all these things stringing out. Does anybody know the cube root of 27?
Great.
Good. And so over here, I'm leaving a gap to pull out more things, and I'm putting a cube root right here. Had this been 54, which is twice that, I would have pulled out a 3 and put a 2 in here. That's my bookkeeping. I pulled out a 3, but I left a 2 inside. I'm leaving a gap here to pull other things out. You see what I'm doing? Just keeping track of each one thing I'm doing. But 3 came clear out, and there are no numbers left, so I'm not putting anything in there. How many x's can I pull out? Be careful now, we're doing cube root. 2, and how many are left? 2. Because there's 8 x's in there. If I circle 1, I circle a triple and another triple, I got 2 left over. Can you imagine that?
Yeah.
So do you understand this? So how am I going to deal with the y's?
3 y.
Absolute value, though.
Y to the 3rd and a y left inside. Can y'all understand that bookkeeping business? This is what I do when I realize there's going to be some leftovers because these are not evenly divisible by 3. I know there's going to be some leftovers, at least in the variables. I work on the number. I write down what I can take out. I put down what's left. There wasn't anything left in the numbers. Then I work on the x's, and I leave a gap here. So I'm writing down what I'm pulling out left, so I only have to focus on one at a time. It's just a quick way to do it. Okay? And you said we need absolutes on this? We do not.
No.
Because when you cube root something, it's okay to get negative results.
Oh.
Remember? This is nuts. I know. It is very, very subtle. You have to really think about what you're doing. So what we've learned here, if you want to conceptualize this, is that if you've got an even root, you better watch out for this and make sure you handle it right. If you've got an odd root, all bets are off. Whatever you pull out is just fine because it doesn't matter if it's positive or negative. We don't care. The cube root of -27, -3, and that's okay. Okay, so we don't care. If it was negative in here, it can be negative out here. It's no problem. All right, now. Okay, the rule is this. If you want to memorize something or write it down at the top of your paper or whatever. If you want to if you don't want to think it through every single time, this is what we've learned here. if you pull out an odd power from an even root, absolute value. If after you pull it out, you have an odd power on something, well, on a variable. If you pull out so that it's an odd power when you pull it out from an even root, you have to force its positivity by absolute value. Any other thing, no absolute value. That's the only condition you need that for. If after you pull it out, the power on it is odd, and you pulled it out of an odd root, even root, flat absolutes on it. Okay? So let's do the ones that they have in the book and see if we can use those properties on there. We've got, the cube root of 64, y to the 6th. So cube root, 64, y to the 6th. First thing you should do is deal with the number and ask yourself this right off the bat. Is 64 a perfect cube?
Yes.
Good, then we don't need to prime factor. We could, if you don't realize 64 is a perfect cube. But it is. It's the perfect cube of what? 4. So I put a 4 here, and I recognize that all of the y's are going to come out because 3 goes into it. But if you didn't, you would put a little thing like this, and you leave a gap here and keep track. There's no numbers left over. So now I'm dealing with the y's. How many groups of 3 y's are there?
2.
Is there any left over?
No.
Okay, so I have y cubed, and that's it. Do I need to absolute value this? Why? Came out of an odd root. Bets are off, right? Oh yes, you're right. It just occurred to me as you said it. Sorry. Yep. That's what I get for talking and doing math at the same time. I never can do it right. So everybody understand why there's no absolutes on that, even though it's an odd power? Because it came out of an odd root, and that doesn't qualify for absolute value. Okay, let's try this one. Let's do the 4th root of x to the 4th over y to the 8th. Okay, you remember the property of division that you can do each of these separately and consider them one at a time? You remember that? Okay, so let's consider the numerator. Pretty easy consideration. What are you going to get?
1 over 10.
You're going to get, how many x's come out of the top?
1.
Any left over?
No.
Okay. How about the bottom? What's going to come out of there?
2 y's.
Y squared?
Yeah.
Okay, now we've done, and there's nothing left. Now that we're done pulling everything out, we have to now see if we need an absolute on anything. Oh, it's possible. We do need an absolute value. It's possible, because that's even. Will any of these have an odd power? Yes, they did. That x has got to be absolute value. Because the power that came out was 1, which is odd. I pulled an odd power. This is an understood 1 right here. I pulled an odd power out of an even root. Qualifies. Needs 1. I pulled an even power out of an even root. It's forced to be positive by squaring. You following me? Everybody got that?
Yeah.
Okay. Now, here's the worst part. Not something you have to learn. It's going to make you go, well. Look at example 7 and example 8. Just read what we're supposed to do. It says in example 7, write each expression in simplest form. Oh, and assume all variables are positive. Well, why do we even learn this? Well, there are certain circumstances when you don't get to assume that. Notice the instructions for number 6 and how they are different. It says simplify each expression. You're not allowed to assume anything, so you have to force it. If you get some instructions on your exercises where it says simplify each expression, assume all variables are positive, now your brain's off the hook. You don't have to do this because we're assuming everything's positive to begin with. And then example 8, look what it says. Perform each indicated operation. Oh, and assume all variables are positive. Well, why the heck did we learn this? For situations where we don't get to assume. So I want you to look at your exercises and see what you're up against there, just real quick, and then we'll learn this other stuff. Page 249. Look at the instructions for number 49. 49 to 54 says simplify each expression. You must consider this in that case because you don't get to assume anything. Then look at the instructions above number 57. Write the expression in simplest form. Assume all variables are positive. There won't be any absolutes on these. But there's likely to be some absolutes on 49 to 54. You understand the difference?
Yeah.
And look at the top above number 65. Assume all variables are positive. So read the instructions carefully to decide if this is going to be an important part of it for you. Especially if you're doing your work on Big Ideas Math, because they're going to expect you to follow the instructions. So if you put absolutes where they don't belong, you're going to miss it and you're not going to know why. And if you fail to put absolutes where they do belong, you're going to miss it. So watch them careful. Be careful with the instructions on what you get to assume and what you don't. Okay, so now on to example 7. It says write each expression in simplest form and assume they're all positive. So I don't need to consider absolutes. So these are a little bit longer, but I've already taught you how to do them. So we're just going to run through them pretty quick, and you are expected to tell me if I'm running over the top of you. So the A part, example 7 says, fifth root of 4. Somebody read that to me after I get up here. It's the fifth root of 4 what?
A
A?
to the 8th power, B to the 14th, and C to the 5th.
Yuck. That's not so bad. Can you see there's not a prayer of having any groups of 5 in that number 4? So I'm going to write down this. I'm dealing with my numbers. There's nothing coming out in the numbers. So now I'm ready to consider the A's. How many A's will come out, if any?
1.
And how many left over?
3.
How many B's?
2. 2. Yeah.
How many left over? Good. How many C's?
1.
How many left over?
3.
Done. It's not that bad, right? You following me?
Yeah.
Okay. And because we get to assume all variables are positive, I don't even have to consider that. I wouldn't anyway, because it's a fifth root. But okay. Now the B part, this is going to get a little bit. X over the cube root of y to the 8th. X over the cube root of y to the 8th. There was no radical on this, right? It was just X.
That's it.
Okay. All right. So I don't do anything in the numerator, but in the denominator, I got to take out, first thing you should do, and I always recommend this, simplify this as much as possible so that what remains is as small as possible to deal with the rest. I would not, for example, I would not multiply this by the cube root of y to the 16th. That would have all the y's come out as y to the 8th. You've got a lot of simplifying to do, and that's not a good thing, okay? So what I recommend you do is simplify each radical as much as possible before you decide what you're going to do with it. So how many y's are going to come out of there?
2.
How many left over?
2.
This is improper because we got a radical in the denominator. So now you got to ask yourself what you did in the previous section. I've got the cube root of y squared. How many more y's have I got to have to get them to come out so that there's no radical left? 1. And the whole subject of this is cube root. So I'm multiplying by the cube root of 1 more y so that this times this can be the cube root of y cubed. You see?
Yeah.
But I got to multiply this by the same thing. So once you made that decision, multiply your numerator as well. So the answer turns out to be x cube roots of y on the top over, now, think about how you designed this. Can you see that this product is a y? And I've already got 2. Y squared times y. You following that? Is that too tricky? You want me to throw an extra step in there anywhere? Anybody? You good? Okay, so that's now rational. We're done. And we get to assume they're all positive, so I don't have to consider that as an absolute thing. Okay, the last one is, this one will be really tricky. 14xy to the 1/3 over 2x to the 3/4 z to the -6. Yep. You look at that and you go, well, there aren't any radicals. Yes, there are. They're just written as fractions. You can write them as radicals if you want, but it won't help you. It's easier actually to deal with these things the way they are. First of all, deal with the big numbers because the big numbers will behave like they always have. That is, 14 over 2 is 7. So we're done with those. We don't have to consider those anymore. I'm just going to cross those out. Now consider your x's. Here I have, you got to remember this. Up here I have x to the 1. and I have 3/4 of an x down, not 3/4 of an x, but I have x to the 1 up here and x to the 3/4 down here. What do you do with things with the same base that are being divided? What do you do with the exponents? Subtract. What is 1 minus 3/4? Is that 1/4 positive? Then it stays here in the numerator. It stays where the bigger one was. Oops, you said 1/4. Okay, x's are taken care of because 1 minus 3/4 is 1/4. There was more up here than there was down here, so it stays in the numerator. Done. Okay, now look at your y's. Well, that's an easy consideration because there's only one and there's no canceling going to happen because there's only one and it stays where it is because it's positive. Its exponent is positive. Do you see? And then we consider the z's. So I considered that. We consider the z's and there's only one of those. But his exponent's negative. So we bring him up here. Done. Did you catch that? Okay, so if you have things with the same base in numerator and denominator, you have to subtract the exponents. And if you end up with a negative, you leave the results downstairs so that it'll be positive. I mean, if this were x to the 1/2 and x to the 3/4, I would have left x to the 1/4 down here because there was more down here. You know what I mean? Okay. So there's that. That's how that one goes. Okay, adding and subtracting variable expressions. We're going to do that next, and it's going to be just like you did yesterday, so it shouldn't be anything new, only we're going to deal with variables. It's a very, very small addition to things. Again, if you'll notice in the instructions, it says we can assume all variables are positive, so there's no absolute values necessary. So here's what we got to do. We got 5 root y plus 6 root y. I'm not going to bother to put that on the board. So that's 11 root y. Just like that. Okay? The other one might need a little more work on it. We've got 12 cube roots of 2z to the 5th. What's the other one?
Minus z.
Minus what?
Z.
Cube root?
Yeah, cube root. Sorry. And
What's
then
that?
54 z squared.
Okay? The way they're written, it's obvious you cannot combine these together. They can both be simplified. So we should do that and see if they are alike, just like you did yesterday. So I've got a 12 that's already sitting out here. Is there anything in this that could come out?
5 is here.
How many z's are going to come out?
1,
1. How many are left over?
2.
And that 2's not coming out, right? There's no cubes in that. So it's cube root of 2. And this is, how many z's?
2 z's.
Okay, I'm getting the same answer from the same people. I'm only hearing a few voices. Do you understand this simplifying? Because if you don't, you need to speak up. Everybody understand why we wrote what we did in the bookkeeping aspect of this? There was 3 z's there. I took 1 out. There was 2 left over. And that 2 never had a prayer coming out. You with me? Okay, let's consider this. We got a 54. We're going to have to look at that number by prime factoring. We got 6 and 9, 2 and 3, 3 and 3. There's a triple. So what gets to come out here is a 3. I already have a z waiting for it, and we usually put that behind, so that's why I'm doing it this way. There's your 3, there's your z, and inside I have this lonely little 2 left over. It didn't get to come out, and that doesn't have enough z's to come out. Did you catch that?
Yeah.
Okay, now, this is where it gets a little weird. It's not just the radicals you have to look at now to combine them. This entire thing has to be exactly like this entire thing. And if it is, then you can take 12 minus 3 of them being the circled red stuff. So now you're analyzing not just what's under the radical, but also what came out as far as variables go. Are they the same? They are. So if you check it carefully and they are the same, then you can take 12 of those weird old things minus 3 of those same weird old things makes 9 of those weird things. We could pronounce it. You'd say 12 of those z cube roots of 2z squared minus 3 of those z times the cube root of 2z squared thingies makes 9 of those z times the cube root of 2z squared thingies. Trick is you got to verify that they are alike before they can be combined. Take some simplifying. Think you can handle that? That's it. Okay, for those of you doing the assignment on paper, here is the assignment. Those of you doing how big that is, it's already available to, I hope. So it is 49 to 55, 57 to 70, 71, 73, 74. Also, if you can do number 40 or do number 77 and show me your work on how you got the answer, it's worth some extra credit on your next test. Not much, a little bit. So if you're interested in extra credit, do that problem, number 77. However, and this is for all of you to listen here, when you do extra credit for me, and I don't assign it very often, but when you do extra credit for me, the problem that you do has to be on its own separate piece of paper. Not really large, you could tear it off of something. You could use one of something up here on my notebook, you could use a Post-it. But it has to be different, it has to be separate so that I can focus on it and make sure I pay attention to it when you turn it in. I don't want to just be looking for extra credit on the back of everybody's assignment. So if you're going to do extra credit, it has to be on its own paper, and you would write 5.2C, number 77, EC for extra credit. And then do the problem, show all your work, and if I'm satisfied you know what you're doing, then you can get some extra points on your test, next test. Okay? All righty. That's it for that one. Good luck.